Okay, mathletes, this lesson is going to examine three word problems out of your textbook and sort of walk through it step by step so that hopefully you can sort of gain a methodology or a problem solving technique to walk through some of these problems. Give yourself a little bit more confidence trying to solve word problems involving quadratic equations. All right, so these three problems, we'll start with number 11, the golden ratio. This seemed to be the first problem on that assignment that people had difficulty with, and I think part of the difficulty is that the question is not really phrased very well. They tell us that this is a golden rectangle. It has this special property that in this golden rectangle, if I take the short side and I make a square inside of the rectangle that remains is similar to the original rectangle. And although this doesn't seem very exciting in any way, it actually has some very interesting properties dealing with fractals and infinity and the golden ratio and all these other things. But the challenge laid to us is to show that the ratio, the golden ratio, using this picture can be found to be this number. And of course we could calculate this to a decimal. It'll go on forever just like pi. And that number is what we normally call the golden ratio. He gives us this hint to let AB equal x and AD equal 1. Alright, so how do we attack this problem? Well, what we're going to do is we're going to take a closer look at this picture. So on yours, in your textbook, if you're following your textbook, look at this picture while I go ahead and try to dissect it over here. All right, so here's the big rectangle, A, B, C, D. They say to make AB x and AD equal to 1, right? So here's AB and AD. And so we're just looking at that big rectangle. Now let's look at this smaller rectangle. And the challenge is to find the dimensions of this smaller rectangle. Well, we should realize that this side is 1 because it's just the opposite side of AD. So BC, it's a rectangle, so it's going to have the same length. This side is a little bit more difficult to see. If from A to B is x, all right, from A to B is x, all the way across is x, how far is it from A to y? Well, A to y is 1 because this side is 1. If this side is 1, this is a square. All these sides right here are equal to 1. So AB is x, AY is 1, so what's left over is going to be the whole thing, which is x minus 1. So this part of it is going to be x minus 1, so I label this as x minus 1. Now these two rectangles are similar. Well, what does that mean? It means that if you match up the sides that go with each other, like if I try to put this small rectangle sort of on top of this big rectangle, the sides that match up should make the same fraction. And so what I've done is I've taken this picture here and I've made it easier to see. So I've just sort of rotated it 90 degrees counterclockwise. So I just kind of laid it on its side. All right, so if these two objects are similar, then all the sides are proportional. That means if I put this x over 1, if I make a ratio x over 1, that will give me the same exact ratio as 1 over x minus 1. Right? They should make the same fraction. So that's what I've done is I've made a proportion. I've said, well, x over 1 should give me the same fraction as 1 over x minus 1. Those two are supposed to be the same, so I'll make them equal to each other and I get this proportion. And that's a huge breakthrough. If you can do that, the rest of this should be simple. All we have to do is cross multiply to make a quadratic, and that's why this question belongs in this section. So now I have this quadratic. How do I solve a quadratic? Well, what we normally do is pass everything over to one side, make it equal to 0 on the other side, and then we can either factor this, which it's not factorable, or we can complete the square, which is not really the best choice. From here we should probably use the quadratic equation. So if you take a moment to do the quadratic equation first, so pause, and then come back and check your answer with me. So hopefully if you substituted in the correct values for A is 1, B is -1, and C is -1, we know that negative B, the opposite of B, the opposite of -1 is 1, and we substitute everything else into the quadratic equation, then we get this term here. We don't have to go any further. The only difference between our answer and the answer in the book is that we have a plus or minus here and they just have a plus, and that's because if we look at the minus root, so 1 minus root 5 over 2, that actually gives us a negative number, so we actually don't consider that as a possible solution, so they're only looking at the positive root here. So we have shown that this number gives us the golden ratio. The golden ratio, the ratio of the sides, of the short side to the long side, or the long side to the short side, is this special number. All right. And there's a lot, if you're thinking about topics to explore, and this is actually a very interesting topic to look at. If you want to maybe possibly think about it for your IA, your exploration, you might want to think about it. Anyway, moving on. Here's number 13. A uniform concrete path is paved around a 30-meter by 40-meter rectangular lawn. So I think the main idea is if you can draw a picture here, that'll give you sort of the best way to formulate the question, formulate the equation. In all these word problems, you should start with a picture, label it as completely as you can, and then see if there's some sort of quadratic equation that you can write that will give you the answer. So go through those steps. Try to draw a picture, label it completely. Pause. Okay, let's see if your picture looks like mine. So it says I have a 30 by 40 meter rectangular lawn. I've been watering it and it's nice and green, and so there's my rectangular lawn, and I'm gonna sadly make a concrete path that goes around my lawn, and it says it's uniform, so that means it's the same width all the way around. Alright, so I don't know what that width is gonna be, so I called it X, but I do know that the area of in white here, the area of just my concrete is going to be 1/4 of the area of my lawn. So how wide does that have to be to make that true? So here's my picture, and hopefully you can figure out a way to write an equation given this information to solve. So pause and see if you can do that now. Okay, so you could break up this frame, this white frame around this green rectangle into pieces and add them all together, but what I think might be easier to do to find the area here is to take the big rectangle, the area of the whole big rectangle, and subtract the area of the green rectangle. So all that will remain is this white frame around, and so that's how I wrote my equation. I said I'm going to take the length times width of my big rectangle minus length times width of the small rectangle is going to be 1/4. So that area, so this gives me area minus this area, so this area of the concrete walk is going to be 1/4 of the area of my lawn. This is the area of my lawn. If you get this, the rest of it should just be mechanical, easy, just crunch the numbers, just don't make any silly mistakes. And so what I did is I got to this point here, and I can see that this is not factorable, so I would have to use the quadratic equation and or a graphing calculator, and so that's what I did. As I went to my graphing calculator, and even though you can't see it, I typed this part of it in to y1, and then I looked at the intercepts, the x-intercepts, and this x-intercept there. So there's a negative number, which we don't consider, so this is a positive number. And so that's how I ended up finding my value for x in this particular case, using the graphing method. Rather than use these big numbers with the quadratic equation, I used the graphing method. All right, here's the last question. Question 50. Now, this is the last question I'm going to cover, not the last question on the assignment. Hopefully, after seeing how these 3 questions have been done, hopefully that'll provide you enough momentum that you can finish the rest of them. All right. Average speed of a small airplane. All right. And so with this one, maybe it's not as helpful to draw a picture, although you might draw a picture anyway, just to figure it out. What I've done is I started with a formula. I know that distance equals rate times time. So I took this formula and I substituted values in that were given to me. So I know that the distance of it is 1,000 kilometers. I also know that that equals my rate times my time, but I don't know what the original rate, so it looks like it's been done sort of twice. The airplane had some sort of original rate and original time that it took to go the 1,000 kilometers. We don't know either of those. And then there's sort of like a second run where it's the same distance, 1,000 kilometers, but this time we're going to go slower, 120 kilometers slower, and it's going to take us a half an hour faster, more, to complete that 1,000 meters. So I've written those 2 equations here. Here's sort of the original one, and here's sort of the secondary one. And so what I did is I saw immediately that these both equal 1,000. So maybe what I can do is I can do substitution. I can make this part equal to this part and start solving. Oh, this is nice because now the RT's cancel out. But then I get this expression. Ooh, that's supposed to be an R. This is supposed to be 0.5 R. So this is supposed to be 0.5 R. And I have an R here and a T here, which means I have 2 variables and 1 equation, and it's not solvable. So you're supposed to see that this is not solvable. So we started off okay. We used equations and formulas, and we started matching them up, but we ran into a dead end. So we need to backtrack and figure out what went wrong. What went wrong is I can't have an R and a T in the same equation. So somehow I'm going to have to get rid of one of them. I have to get rid of an R or a T and just have one equation with all R or all T. And since we're looking for the speed, hopefully we'll find R. The rate and speed are the same thing. So the speed of the plane, the rate of the plane, that's what I'm looking for. So what I've done is I've taken a look at this equation and I solved for T. So distance equals rate times time. Here's my original, one of my original equations, and I've transformed it. So I just divided both sides by R. Now what I can do is I know that T is equal to this expression. So wherever I see a T, I can substitute this in its place instead. So instead of this T right here, I can put 1,000 over R instead, and that's what I've done. Everything that you see in this equation here, I've rewritten exactly the same. The only difference is instead of T, I've put this 1,000 over R instead. And now I've got one equation with just one variable, and as daunting as it looks, it is solvable. So I just set out to solve it one step at a time. Then I get to something like this, and then I decide I don't like this fraction here, so I'm going to multiply everything times R, and voila, this is where we finally get our quadratic equation. So that's how this linear equation becomes a quadratic equation. I multiply everything times R to get rid of my fraction, and not only do I do that, because this is a fraction, I don't like that, I multiplied everything times 2. So now I have this resulting quadratic equation. It looks pretty nasty. If you look at it, it's not factorable, unfortunately, so that leaves us the quadratic equation. These are some really big numbers. And so what I did is I went to Wolfram Alpha and I typed it in, and I got this as my solution. This is of course the exact solution, which means no decimals. So this has no decimals, but this is a word problem that needs decimals, so I hit approximate forms, and this is the answer that it gives. We don't need the negative root, so we stick with this 553.56. Three significant figures just means 553, so my final answer is 553 kilometers per hour. Don't forget your units. Right? So that's the speed of the airplane, the original speed of the airplane. The first time it went and flew was 550 kilometers per hour. Okay, hopefully that was helpful, and you can use this to solve the rest of the equations. Right? Use a formula, use a picture, and good luck.